everyone. This is Matt Heywood. I'll be doing the presentation for Team 3, which consists of myself, Amanda Howell, Ryan McQuaid, and Tony Voice. Our project focuses on pasture rotation. So just quick, a little executive summary for you. Our main goal was to allow ranchers, farmers to maximize profits while reducing costs. So this is achieved through buying less feed and hay, by also maintaining cow health and calf growth, so on and so forth. So this is best achieved by utilizing existing grass and pasture rotation schedules without buying new feed. So we built a model to simulate this rotational grazing system. We have pastures that are divided into subpastures, which we decided to call paddocks. And we're trying to figure out the optimal length of time for cows to remain in a pasture. So A, they can still get fed and get their energy needs, and B, the foraging, the grass, doesn't die off to where the rancher needs to replant more and losing a pasture for feeding purposes. So really, grazing management entails adjusting the number of grazing animals on a pasture at any one time. So two tools that influence our animal output are the concentration of animals per acre, the stocking rate, as well as the system of grazing management. Through our research, we found that pasture rotation is clearly beneficial, but it's not an exact science. There are many variables to consider, such as the number of days to leave an animal in a pen, the best pen size, how rainfall and fertilization affect the length of time an animal can spend in a pen. So it's just these bioeconomics make the decision-making process very tough for ranchers and farmers that are running a dairy or a pure beef ranch. But simulation research, as we found out, can shed some light on this issue. So our approach was to take a multi-agent scenario-based approach and basically breaking it down to looking at cows as well as nursing cows, since they obviously have different energy needs. Outcomes, obviously, it's not a perfect approach to time-controlled grazing, but having some sort of time control management system does allow for better land health and therefore hopefully some cost savings. Okay, so an introduction to our system, some of the components. The agents we used are nursing and non-nursing cows, as mentioned before, grass, water. Now, all these agents are autonomous, so they peruse their own objectives, which can affect the other agents, but they don't directly communicate with each other. So, as I said, the neighbor agents can cause adjustments to agents' behavior, but they do not communicate to do so. It's just the actions can cause these changes. So an important issue for our system, obviously, is the management of land. And the big problem here is, how does grass, cows, and farmers change and adapt to external conditions such as rainfall? If it's raining too much, it could wash away the grass. If it's not raining enough, you could lose grass just from natural attrition. So our model is concerned with interactions of these multiple agents. We're going to examine these interactions to observe what each agent does given a set of conditions. So the purpose, again, is to see what happens when simple behaviors interact in complex ways over time. So our primary research goal for this project was to construct a model that determines optimal length of time for cows to occupy a pasture to get the greatest possible forage intake without damaging the grass to the extent that it doesn't recover. The model was built the model was built combining two existing models with original code written by our team members. So the first model that we kind of picked apart and used in our code is a NetLogo grazing model #1 by Peter Donovan. This code provided code for us to use for growing of grass, the grazing of cattle, and the energy that the cows get from the grass. It also had plotting to show the gain or loss of money per day versus health of grass. So pretty useful stuff. We also used part of the many regions example from the NetLogo library to create our paddocks. So we had some sub-questions, such as how does rainfall amount affect grass health? How does the number of cows nursing calves affect the amount of grass needed? As well as, does pen size exponentially affect the number of animals a rancher can maintain? So we'll hopefully answer some of these through our study. In our system, it's an agent-based design. The grazing simulation model, or GRASM, if you will, it's designed to model water nutrient cycling as well as vegetation dynamics of a typical pasture system with multiple paddocks. It features three built-in grazing schedules. One simulates grazing using a put and take method. The other is rotational grazing based on a fixed time duration. And the final is rotational grazing based on forage availability. So the model can predict grass growth, estimate the quantities of water. It also helps farmers make comparisons and management options to maximize forage accumulation while minimizing nitrate leaching on a whole farm scale. The GRASM it's comprehensive and links all components of the pasture system together. Reason being is that you can just use this to better understand the pasture system to determine the management strategies that will yield farmers, ranchers, the most efficient utilization of their pastures. It also generates information to help estimate financial and environmental impacts of dairy management strategies. Our system is designed as a tool to simulate intensive rotational grazing management. It accounts for various budgets in the pasture environment. So some of the data that we needed to go into the system are, min and max temperatures of the weather, rainfall amount, average daily solar radiation, soil properties, grass growth parameters, soil nitrogen transformations coefficients, initial levels of soil, water, and nitrogen. So that went into our model and some of the variables we had. So the output we get will be daily biomass production and the water and nitrogen levels in different pools. So some of the variables used, again, are the grass biomass, grass growth rate, leaf area index, soil moisture content, soil nitrogen content, plant residues, and organic matter. Again, this is based on the GRASM we found in our research. So the steps of this type of model. First, you got to determine the number of animal units in the grazing system. You then have to estimate how many acres will be needed throughout the grazing season. You then estimate how large each paddock should be, and finally you must estimate the number of paddocks needed. This should provide great insight into the cost savings and benefits to using a system like this to make farm management more efficient and profitable. So, just a few examples, discussion on the design of our intelligent agents. They revolve around environment, performance, sensing, and acting. So the environment in our model is the pen and grid size of the world. The ability of grass grow after being grazed will be determined by sliders. So the slider values are based on some of the equations we came up with from the other models and our research. The model measures the performance of health of grass and cows based on a few variables, which are, again, rainfall and number of cows grazing at one time. Cows not concerned with other cows, as I mentioned, but they will sense the amount of energy each patch of grass will provide. So again, they don't communicate directly, but they can tell what their environment is giving them in terms of information. A cow's actions will indeed directly affect the patch it is on. As it eats, the patch will lose more grass. So the types of agents we use in our architecture: cows, nursing cows with calves. Those are two agents. Then we also have nursing cows in gestation, so they have not given birth, but they have the fetus still in their system. So all these are represented by breeds in the model. That's the terminology we used for the model. Just again, another point on agent communication. Cows will not communicate in our model, even though they do communicate in real life, especially around breeding. But since ours is based on grazing, we didn't feel that we needed to complicate things by adding in communication between the cows. All right, so in the model, as you can see, you get a little screenshot of the model here. You can see the sliders and the output as well as the charts. So in the model, users are able to toggle the number of pens, the number of cows per pen, and the amount of rainfall. Using this information that can be found at places like J.C. Williams, we can then determine how much grass cows eat during a specified amount of time and how much rainfall affects grass growth. So to help answer our research questions, our model has three breeds of turtles as previously discussed: the cows, the calves, and the nursing cows. Breeds will eat at different rates. Grids are sectioned off into pastures with cows bounded to them. So we have sliders, as mentioned before, for rainfall adjustments, energy cows receive from the grass, the number of nursing cows and non-nursing cows, and the max and min height of the grass growth. So all these are toggles within the model. So just going into a little system analysis over our model again. So just some of the terminology. The grid is our pasture. Rainfall represents rainfall amount, so increasing or decreasing will affect how fast the grass can recover. Bite size is equal to how much a cow consumes in one day. So cows that are nursing a calf, their number is increased since they have additional mouths to feed. So num cows equals the number of non-nursing cows to be used in the model. Num nurse cows, therefore, is then the number of cows nursing a calf to be used in the model. Update patches, what this does is, does the user want to see grass turn colors based on its health? Selectivity, how picky the cow is about the grass she eats. Graze period is the length of time in days to leave the cows in a paddock. Paddock num is the number of paddocks to be used in the model run. Pasture size is grid size. And, we have constants such as 10 nursing cows. This is just an example. If you had 10 nursing cows, everything else except graze period are constant. And just some numbers to throw in there to see what results you can get if you plug them into our model. So some of the tests we ran, sub-question 1 here, compare the needs of differences between non-nursing cows, nursing cows, and the combination. So the constant we used in this test were all variables except for the cow types. Then we then ran and got results when the sliders were set for 10 non-nursing cows, 10 nursing cows, plus an even split of 5 non-nursing and 5 nursing cows. So our second sub-question and test was to see rainfall's effect on grass growth. Constant here, 10 non-nursing cows, and everything else except the rainfall slider. So we ran tests with the rainfall slider set at 1, 2, 3, 4, and 5. Third sub-question test here is paddock and pasture size effects. So the constant, 10 non-nursing cows, everything else except paddock num and pasture size. So you had some 2 variables to play with in this one. And we then ran the tests at these different settings for paddock num. Sub-question 4 was an invalid included for test 1. We initially set this one up with 5 nursing and 5 non-nursing cows using 4 paddocks, as you can see represented in the graphic. And in this model, within a year's time, the dollars per week dropped below the average biomass. So some design rationales to explain why we went about the model the way we did. We tried to use as many real-world variables as possible without making the model too complex. Now, obviously we could have thrown more things in there, but for the sake of time and the course scope, we decided to keep it simple, stupid. So we decided on including nursing cows and non-nursing cows because in the real world, a rancher would have both on the ranch. But we did leave out the feeding of hay to keep the model, again, as simple as possible and just focused on the cow's consumption of grass. So here's some of the evaluations of the questions. Feel free to look through them. So these come from NetLogo, the model we built, and then exported it to Excel. So this first test we're looking at here is for grace period. So at a grace period, we set the values we could change and receive the following output, plus a chart of the mean energy versus biomass for 1 year. Our test 2A, again, this comes from NetLogo, exported to Excel, was looking at a test of non-nursing cows and how that would impact a rancher's grass availability based on rainfall, so on and so forth. Test 2C was using a combo of cows, so the 5 and 5 split, and again, we received output for the constant set as well as the variables we plugged in. Third test, again, it's another output from our NetLogo model, and this was looking at how rainfall can impact graze periods, the health of the grass, and ultimately how well cows can restock their energy. Test 4A, another one coming from NetLogo exported to Excel, looks at paddocks and pastures. And we have charts here to evaluate mean energy versus biomass for 1 year in regards to having 3 paddocks, so pasture size. Test 4C again looked at paddocks and pastures. Just a few different variables toggled for this one, so we just wanted to see how it could change the outputs. So some lessons learned from this. I mean, grazing management can lead to lower feed costs by cutting harvested feed sources to increase profitability. I mean, that's a fact. Getting to that point isn't as easy, but using a simulation model like we created can definitely help ranchers get there. So it helps you to focus on the management and control of production and pasture resources, which in turn is a cost-reducing strategy. A well-managed rotational grazing system can reduce or eliminate the need for labor-intensive or purchase inputs such as supplemental feed, nitrogen fertilizer, and weed and brush killers. So it really is key to get that rotational schedule nailed down to a science. Because since feed costs are the major costs in almost all livestock operations, getting a control of them or being able to cut them is surely critical. Other lessons learned, I mean, to minimize overgrazing and undergrazing of foragers on intense rational grazing system, it's ideal over continuous grazing. So to minimize overgrazing, it's all about intense rotational grazing schedules. This could help to lead to better pasture management and again, cutting costs over just letting them graze until the grass is dead. So the rotational system definitely provides a rest period for forage plants so they can grow and recover. This rotational system also provides opportunities for moving livestock based on forage growth, shifting them to an area of pasture that has more grass to allow an area with less grass to recover. Obviously, this promotes better pasture forage utilization, and it can extend the grazing season because all of the grass won't be killed off. Thanks for watching. If you have any questions, please leave them in the comment of this video. Again, this is Matt Heywood for Team 3, presenting our grazing rotational simulation model.